So far we have been looking at control volume analysis, which means that we take this big microscopic volume and we want to look at the forces the forces acting on the control volume, which requires us to look at stuff entering and stuff leaving the system. So we are mainly focusing on what's going on at the boundaries, unless it's some kind of unsteady situation, in which case we are also looking at rate of change inside the control volume. But more or less we have focused on just the surface fluxes, what's entering, what's leaving, how much momentum is it carrying in or out, how much energy is coming in or going out. This is fine if we are looking at some kind of overall system balance, or if our control volume analysis is required to help figure out, let's say, force on a body like a turbine vane that we discussed earlier. So for things like that, that's fine. But if we want details of the flow, if I want to see how things are varying, let's say we have flow going on. So we looked at something like this earlier, where we had flow entering our control volume, which was this. It was something like that. And we looked at flow entering, we looked at flow leaving, and then we said, okay, well, that's exerting a force in the rightward direction, and so to keep this fixed, I had to apply a force in this direction, and I had to apply a force in that direction, and so on. So if I wanted to find out Fy and Fx, then the control volume is great. But suppose I wanted to do more than that. Suppose I wanted to find out what's happening to the velocity as it goes from V1 to V2 through this control volume. If I wanted to find out details of this flow at some distance s along the path, then the control volume doesn't do such a great job. Well, I could always redo the control volume analysis by just taking this as my control volume and figuring out, if I have V1, then what's the new V sub s, let's say. But that gets a bit tedious. So what we are going to do today is look at the differential mode of analysis. So I essentially, instead of writing out the integral form, which is the control volume analysis, I write out the differential form of the same equation. And so we are going to look at differential analysis of the system. And so what this essentially means is we redo the same thing, except now that we replace, as you might guess, integrals with differential equations. So now our control volume is going to look really small. It's going to be tiny. We are going to assume that things are changing very slowly, or slow enough that a derivative can, a single first derivative can approximate that rate of change of a quantity, which could be velocity or density or energy. So let's say I have a coordinate system, x, y, z, and I want to derive an equation, a differential equation that lets me express my conservation laws for mass, momentum, energy. The point of doing that would be that for any unknown control volume, I could just integrate this out and get my quantities at whatever point. So let my control volume have dimensions delta y, delta x, delta z, and I now want to express my, let's say we'll start with mass conservation. So the Reynolds transport theorem in integral form would have said del by del T of my rate of change of mass in the system plus the mass fluxes entering or leaving the system. That should be 0 because there's no net change, or rather mass is not created or destroyed. So what we're going to do is rewrite this in differential form, essentially. Now, one could do, this essentially follows from Gauss's divergence theorem, which we took a look at in the very first week of class. I could apply Gauss's divergence theorem and I could directly write this out and say, and get the final form. We are not going to do that because that while that's mathematically correct, it doesn't really give us insight into what's going on. So we'll derive the resulting equation in a different way, but I'll just make a note. Gauss divergence theorem but we want to do it a different way, so I'll just erase this to create some space. Okay, so let's look at mass entering the system. So if I had U entering the system through phase delta, through a phase with dimensions delta Z, I'm sorry, that should be a V. So if I looked at mass entering the system in the y direction, it has to do it through the phase with unit normal in the y direction, which is delta x, delta z. So let's say it has a velocity v entering this phase and leaving this phase is v plus delta v. Similarly, let's see, if I had a mass, a velocity w entering the phase with dimensions delta x, delta y, it would be leaving with w plus delta w, and I'll call this w here. And there is a third phase which is into the plane, if you will. So that would be going into this phase, and that would be u, and it would be coming out at u plus delta u. And there's also a change in density. If I'm observing the system for a time delta t, there might be a change in density, so the overall mass of the system might itself change. What conservation expresses is the fact that the sum of the mass fluxes entering or leaving plus whatever is being plus whatever is being stored, or rather the rate of change of mass in the control volume is the net sum of whatever is entering minus whatever is leaving. So the mass of the system itself is rho dV, and so that's rho delta x, delta y, delta z. Okay, so let's go and find what the mass fluxes are that are entering or leaving the system from each of these phases. So we have the phases marked here, so V is entering the phase with dimensions delta x, delta z. U is entering the phase with dimensions delta y, delta z, and W is entering the phase with dimensions delta x, delta y. So the fluxes, for example, entering through the phases with normals in the x direction So let's look at the flux entering. The flux entering in the x direction would be rho u times delta y, delta z. And the flux leaving, I'll just put a minus sign there to find the net flux entering. So the flux leaving would be rho u at the other phase, so this is in and that's out, times delta y delta z, and I'm going to say that this could be written as del by del x of rho u times delta x, delta y, delta z. So that's a del by del x of rho u times delta v. That's the net flux entering in the x direction. If I, and so you'll have to edit out that whole screen, right?
Yep.
When I swipe, it showed up. Yeah. The net flux entering in the y direction would be similarly rho v times delta x delta z, that's the flux entering, minus rho v leaving, and I'm just going to once again approximate that as del by del y of rho v times delta y delta x delta z, and so that's a del by del y of rho v delta v. And similarly in the z direction, it's del by del z of rho w delta v. That's the net flux, or rather the net mass flow rate entering. So now if I want to perform a mass balance, I need to essentially say that whatever the mass is that's entering through these phases is equal to the rate of change of mass of the system. And the rate of change of mass of the system is just del m by del t. So rate of change of mass is del by del t of rho delta v, and that should be equal to the sum of these fluxes. And it looks like I forgot a minus sign everywhere. We have a minus sign here as well. So the rate of change, this needs to be equal to minus del by del x of rho u delta v minus del by del y of rho v delta v minus del by del z of rho w delta v. I cancel out the differential volume. What I'm left with is del by del t of rho plus del by del x of rho u plus del by del y of rho v plus del by del z of rho w equals 0. We'll make life simple for ourselves and say that we are looking at incompressible fluids, so my density is not going to change with time. So this term, this first term drops off, rho comes out of the partial derivatives in space, and because it's a prefactor that's constant, we can drop that too. And so for constant density, which is what we are mostly going to consider, this becomes del by del x of u plus del by del y of v plus del by del z of w is equal to 0. If we further say 2D flow, so that there is no w component, this essentially becomes del u by del x plus del v by del y equals 0. This is what is called the continuity equation. in differential form. And that's just mass conservation really.